This problem is worth 16 marks. The first two problems, A and B, are on this slide, and the next can be found on the succeeding slides. Consider the sum A equals ln2 plus ln2 squared plus ln2 cubed plus so on and so forth until ln2 raised to 20. Problem A, we explain what the series is arithmetic. The series is, or the sequence is, series or sequence is arithmetic if we can find a common difference. So we find the common difference by subtracting the first term from the second term or the second term from the third term. So the solutions are here, and you can see that in all cases we have the same d or common difference, which is equal to ln2. So we can say that the series is arithmetic because it has a common difference, which is equal to ln2. Find the sum A in the form of A ln2. There are two formula for finding the sum of the arithmetic sequence. I used here the formula that has first and the last term in it because they are given. So substituting the values in that formula, I have the pairing 20 over 2, which is 10. And then the sum of ln2 and ln2 raised to 20 is equal to ln2 raised to 21. Okay, so we simplify this because it must be in the form A ln2. So the final answer for this part is that the sum of the first 20 numbers equals 210 ln 2. Next, we find the sum of A correct to 6 significant figures. So we simply multiply 210 by ln 2 and we get the decimal equivalent. But we have to express our answer what the problem requires, and that is 6 significant figures. Our final answer will be or is 145.561. For problems C and D, we consider the sum B equals ln2 plus square of ln2 plus the cube of ln2 plus so on and so forth until the 20th power of ln2. We explain why the series is geometric. The series is geometric if we can find a common ratio, and the common ratio can be found by dividing the second term by the first term or the third term by the second term. And in all these cases, you can see that we obtain a common ratio consistently equal to ln2. Therefore, the series is geometric, and it has a common ratio equal to ln2. Letter D, we find the sum B correct to 6 significant figures. So we use the formula for geometric series, and then we substitute all the values for u sub 1 and r. And then using our GDC, we'll obtain an answer like 2.2574109 or a lot more digits depending upon the setting in your calculator. But we only need the sum to be expressed to 6 significant figures. So our final answer is 2.25741. The following design consists of rectangular boxes of lengths ln2, square of ln2, cube of ln2, and so on, and the length is expressed in meters. The diagram is shown here in this slide. Okay, our task is to explain why such design cannot have a total length of 3 meters. So finding total means finding the sum of the geometric sequence. And this pattern, since this pattern is kind of an infinite sequence. So we find the sum of the infinite series using the formula u sub 1 over 1 minus r, and then we substitute the values for u sub 1 and r. This qualifies for an infinite sum because the value of our r, which is ln2, is approximately less than 1. Okay, so your calculator will display something like 2.2588914 and so on, depending upon the setting in your calculator. And if you round this off to three significant digits, our answer is 2.26. So even if the sequence goes on and on, the sum will have only a maximum approximately equal to 2.26, and 2.26 is less than 3 meters. Therefore, it cannot really reach 3 meters. The following design consists of rectangular boxes of length ln2, square of ln2, cube of ln2, and so on, and the length is expressed in meters. The diagram is shown here to illustrate the problem. So our task here is to explain why such design cannot have a total length of 3 meters. To find the total length is to find the series or geometric sum. And since the pattern goes on infinitely, we can use a formula for sum of infinite geometric sequence. And this problem qualifies for that because our R, which is ln2, this has been solved previously, is approximately less than 1. So we substitute the values for the formula. Our u sub 1 is ln2 and our r is ln2. It gives us a decimal number which is 2.2588914 and so on. And to three significant digits, it's equal to 2.26. So even if the sequence goes on infinitely, you will only have a maximum of sum approximately equal to 2.26 meters, and 2.26 is less than 3 meters. Therefore, it cannot have a total of 3 meters. For 16 marks, we solve this problem. The admissions team at a new university are trying to predict the number of student applications they will receive each year. Let n be the number of years that the number has been open. The admissions team collect the following data for the first 2 years and they are given at the table. The questions can be found on the next slides. It is assumed that the number of students that apply to the university each year will follow a geometric sequence U sub n. Please remember this very well, that U sub n is a geometric sequence that refers to the number of students that apply to the university, because you will be using this later on in the succeeding problems. Okay, problem letter A, we calculate the percentage increase in application from the first to the second year. So you can go back, you can pause this, you can go back to the previous slide to get the data. Anyway, the solution is here to find the percentage increase. We get the difference of the first and the second year, and then we divide that by the original, the starting year, and then we multiply that by 100%. So the answer is 3%. So that's the increase every year. Now, we write the common ratio of the sequence is only 1 point because it's very easy. So 3% increase plus 100% of the previous, that gives you 103% or 1.03. If you know the R, then you can find the expression for the term U sub n. So we substitute the values in the formula. Our U sub n is the U sub 1, which is 12,300, times the r raised to n minus 1. So times 1.03 raised to n minus 1. That is our U sub n general formula. We will be using that later. Okay, for part 3, we find the number of student applications the university expects to receive when n equals 11. Express your answer to the nearest integer. So U sub 11 is equal to 12,300 times 1.03 raised to 10, and that gives us approximate value of 16,530 when rounded off to the nearest integer. In the first, there were 10,380 places at the university available for applicants. The admissions team announced that the number of places available will increase by 600 every year. Let V sub n represent the number of places available at the university in year n. For the first 10 years that the university is open, all places are filled. Students who receive a place each pay an $80 acceptance fee. When n equals k, the number of places available will, for the first time, exceed the number of students applying. Some of this information may not be needed for these problems C and D. Okay, so but that will be used in the later problems. For letter C, we write an expression for V sub n. So V sub n, as you can see, is an arithmetic sequence problem because the increase is constantly 600 every year. It's just adding 600 every year. Okay, go ahead and get your formula booklet and see how to express the term in arithmetic sequence. Okay, anyway, the solution is here. V sub n is equal to, this is a substitution to the formula that you have in your formula booklet. So V sub n equals 10,380 plus n minus 1 times the difference, which is 600. And this simplifies to 9,780 plus 600n. Okay, we're only looking for an expression in terms of n. This is now your general formula for V sub n. Please remember this. We will be using this later on. Okay, letter D, calculate the total amount of acceptance fees paid to the university in the first 10 years. So in the first 10 years, you are going to get a sum of all the students paying that particular fee, and that fee is $80 per student. So that will be the fees paid times the sum in 10 years. Okay, substituting that to the formula that we have 80 times 5 is obtained by dividing 10 by 2, which is in the formula. And then 2 times, this is in the formula also, 2 times the first term plus n minus 1 is 9, 10 minus 1 is 9, and the difference is 600. So this gives an answer which is equal to $10,500,000. For problem letter E, we find K. Here is where we're going to use the information in that problem. When n equals k, the number of places available will, for the first time, exceed the number of students applying. So there are more places than there are number of students applying. And our number of places is termed as V sub n, and the number of students applying is U sub n. So we substitute the general formula for this, and we have 10,380 plus 600 times n minus 1, if you still remember that. And that should be greater than the U sub n, which is equal to 12,300 times 1.03 raised to n minus 1. And using your GDC, not numerical solve, this gives us n equal to 12.495301 dot dot dot, or a lot more, and n equals 13. So therefore, since n equals k, k equals 13. So on the 13th year, that is the first time that there are more places available than the number of students applying. So for letter F, we state whether for all values where our n is greater than k, will the university will have places available for all applicants? Then we justify the answer. So we know our k is 13. How about if we try 14? That's greater than 13, right? So if our n is 14, we shall have v for v sub 14 greater than u sub 14. We can try that also with 15, 16, 17, 18, 19, 20, 21, 22, 23, and all of them will give you an answer where our v sub n more places than the number of students. V sub n is greater than u sub n. But when you try n equals 24, there is a switch. Your v sub n now is less than u sub n. So few places more students applying. And from there on, the pattern goes on that there are less places, more students applying, or there are more students applying that the university cannot accommodate it anymore. So the answer here is no, because when our n is greater than or equal to 24, our u sub n is greater than v sub n, meaning there are more students applying and there are less places available. However, this kind of solution requires much time. There is a better method using your GDC on how to make these things easier for you. So you can see that on the next slide. So here is how your calculator is making the calculations easy for you. In the first column, inside the formula bar, this is in the formula row, you encode the formula for V sub n. So go ahead and look at the formula. I think that is in the previous slides. So how do you do this? You press menu, data, generate sequence, and this will require you to encode the formula for V sub n. And then you just go to OK, and when you hit that, it will give you the list of the sequence from the first term up to the last term. If there are 255 terms, then there are 255 terms in this column. You do the same for for column B. You use the formula for U sub n. Now you can see here that uh, from first term up to the 12 terms, uh, V sub n is less, but it is only on the 13th term that you first have a taste of V sub n greater than U sub n. And you can scroll it down until, look at the next picture, until 23rd. So on the 23rd term, you still have your V sub n greater than U sub n, but when you reach n equals 24, you have your V sub n less than U sub n. You look at the value, 24,180 is less than 24,275, and you can scroll down, and the patterns remains to be that the V sub n is smaller than U sub n. So you practice doing this. So if you encounter this problem in the next exercises, you'll be able to answer this as quick as possible.